Okay, this session will give some commonly used criteria to define and describe the short-term strength mechanical behavior of thermoplastic material. Okay, first we will look at the tensile properties. So tensile properties are measured in a device that stretches a molded test bar between two clamping jaws. So I'm sure that all of you have experienced how to run the tensile machine. So the jaws separate at a steady rate and the device records the force per cross-sectional area, which is stress required to stretch the sample from 0% elongation to break. And the results are often graphed as stress versus strain. Okay, this figure show the kinds of stress-strain behavior exhibited by plastics. So rigid plastic exhibit a nearly linear behavior similar to metal. Here we can see this linear um, cast polyester non-reinforced produce rigid linear graph, linear line. So the ductile material display a more complex behavior. Okay, you can see that this is a ductile material and the shape is quite complex. Okay, while this figure, it shows the transitional points in the stress strain behavior of ductile plastic. So we can see that at point A, it is the proportional limit, shows the end of the region in which the resin exhibit linear stress strain behavior. Kita tengok dekat sini proportional limit, dia still dalam bentuk linear. So what is a proportional limit actually? So proportional limit is the greatest stress. Okay, dia value the greatest stress at which a material is capable of sustaining a load without deviating from the proportionality of stress to strain, whereby it is the point where the slope begins to change and linearity end. Okay, so dekat sini adalah point yang last dia dalam bentuk linear. Okay, so point B, which is the elastic limit. Okay, what is the elastic limit? And it is the point after which the part will be permanently deformed even after the load is removed. So applications that cannot tolerate any permanent deformation must stay below the elastic limit. Okay, untuk C, C is the yield point. This is the first point on the stress strain curve at which an increase in strain, occur without increase in stress. So the slope of this curve is said to be at 0 at this point. So it is actually the mark, the beginning of the region in which ductile plastic continue to deform without a corresponding increase in stress. Okay. Increase in strain. Tapi kalau kita tengok sebenarnya dia adalah increase in stress. Okay. Increase in stress. So next is the elongation at break. Elongation at yield. Okay. Elongation at yield give the upper limit for application that can tolerate the small permanent deformation that occur between the elastic limit and the yield point, but not the larger deformation that occur during yield. And the last one, point D, which is the break point, is to show the strain value when the test bar breaks. Okay, I'm sure you have familiar and you have dah khatam kot benda ni semua. Okay, proceed with the tensile modulus. Okay, tensile modulus commonly used in structural calculation. Okay, so what is the tensile modulus for? Okay, it is the value that measure the material stiffness. So higher value indicate the greater stiffness. Because of the plastic viscoelasticity Viscoelastic behavior, determining the tensile modulus is more subjective and less precise for plastic than it is for metal and most other material. So mathematically, we can determine the tensile modulus by taking the ratio of stress to strain as measured below the proportional limit on the strain curve. So when dealing with material with no clear linear region, we can calculate the modulus at some specified strain value, typically at 0.1%. So for some application, buckling analysis, for example, it may be more appropriate to derive a modulus from the slope of a line drawn tangent to the curve at a point on the stress strain curve. Okay, so di sini kita akan penting tensile modulus untuk kita measure dia punya stiffness of the material. Okay, the tensile stress at yield is the stress level corresponding to the point of zero slope on the stress strain curve, and it generally establishes the upper limit for application that can tolerate only small permanent deformation. Okay, tensile stress at yield, kita tengok dia punya point dekat yield tadi. Ni dia point kan. Dia punya tensile stress at yield ni sebenarnya rumus dia adalah maximum load over the cross-sectional area. Okay, kalau tensile strength at break, load at break over cross-sectional area, so tak sama. Kalau yang Y dia ada maximum load. Kalau at break tu dia punya load at break je. So biasa tensile strength at Y ni kita ambil yang tinggi sekali, Y yang tinggi. So yield point tu sendiri, kita dapat point tu when the material continue to elongate ataupun dia strain with no increase in stress. So when this takes place, the material yield, or in other words, is permanently deformed by elongation. Di mana dekat point yield point tu, dia memang value dia maximum, dia dah permanent deform. So stress dia kita fixkan dan dia punya material tu dia elongate lah. So the tensile stress at which yield take place is called the yield stress. And kalau tensile stress at yield tu kita ambil maximum load tu bahagi dengan cross-sectional area. Okay, the tensile stress at break is defined as the stress applied to the tensile bar at the time of fracture during the steady deflection rate tensile test. So the data for tensile stress at break establish the upper limit for two types of application, which is one-time use application that normally fail because of fractures, and application in which the part can still function after undergoing permanent deformation. Itu function dia. Walaupun dia dah permanent deformation, dia punya plastik tu dia boleh stay function lagi. Okay, ultimate strength. Ultimate strength measure the highest stress value encountered during the tensile test. This value should be used in general strength comparison rather than as design criterion. Ultimate strength is usually the stress level at the breaking point in brittle materials. For ductile material, it is often the value at yield or break. Ultimate strength ni dia kita ambil value yang maximum stress per material withstand when subject to a load. Dia tak sama dengan yield strength. Yield strength ni value dia yang lepas dia beyond the elastic limit. Tak sama. Okay, Poisson ratio. It measures the ratio of lateral to longitudinal strain as the material undergoes tensile loading. So Poisson ratio usually fall between 0.34 and 0.4. 0.35 and 0.4 for engineering resin. So some elastomeric material approach the constant volume value of 0.5. So Poisson ratio ni sebenarnya dia adalah constant used for determining the stress and deflection properties of plastic structure, such as the rotating disc or plates. So it compare under load the lateral compression strain versus the longitudinal stretching strain or test bar. Formula dia lateral strain bahagi dengan longitudinal strain. Okay, for compressive properties, under equivalent loading condition, plastic tend to fail in tension rather than compression. So for this reason, it is more common to test tensile properties rather than compressive properties. So as a rule of thumb, plastic tend to be approximately 30% stronger under compressive load. So biasanya untuk most material, compression and tension curve ni are almost identical. So tension value are the one reported compared to the compressive properties. Okay, next, flexural modulus. Okay, flexural modulus is defined as the ratio of stress to strain in the elastic region of a stress-strain curve derived from flexural testing. Flexural modulus measures a resin stiffness during bending, and a test bar subjected to bending loads distribute tensile and compressive stress through its thickness. So we can determine the bending capability of a plastic by flexural testing. So basically a specimen is placed across two beams and a force is directed from the opposing side. Okay, coefficient of friction is the ratio of friction force, the force needed to initiate or maintain sliding to normal force, the force perpendicular to the contact surfaces. And the coefficient are commonly listed for two types of friction, which is static friction, which is the force acting on the surface to resist initial movement, and dynamic friction, which is the force acting between surfaces that are already sliding. Okay, we proceed with the long-term mechanical properties. So time and temperature affect the long-term mechanical properties of plastic because they affect polymer chain mobility. And the plastic under constant load tend to deform over time to redistribute and lower internal stresses. The mobility of polymer chain determines the rate and distress redistribution. And higher temperature will increase the free space between molecules as well as the molecular vibration energies, resulting in a corresponding increase in polymer chain mobility. Bila increase the temperature, dia punya free space volume dia akan meningkat, and then dia akan vibrate lagi kuat, so dia akan meningkatkan pergerakan polymer tu. So even at moderate temperature, polymer chain can reorientate in response to applied load if given enough time. So long-term mechanical properties involve the creep and stress strain relaxation. So creep is the added deformation that occur over time in part under constant stress. Kalau stress relaxation is the reduction in stress in part subjected to constant strain. So the creep properties and stress relaxation we have covered in the previous chapter. So we look at the creep properties. Over time, parts subject to a constant load often distort beyond their initial deformation. So they will creep. So long-term creep data help designer estimate and adjust for this additional deformation. So a common creep test involves hanging a weight axially on the end of a test bar and monitoring increase in the bar length over time. Here we can see this is the graph for creep and recovery of macrolon polycarbonate. Okay. So another popular from for creep data is the isochronous stress strain curve, which is plot tensile stress versus strain at given time increment. And we can see this figure about the isochronous. And to determine the apparent modulus or the creep modulus, divide the calculated stress by the resulting strain. Okay, kita dapatkan value stress by strain from the isochronous